Okay, we talked about what first derivative test is yesterday. Tell me how you can tell from the first derivative where a function's increasing.
Well, basically at all the points where the derivative it can be zero, that's where you would have some kind of important point, like a maximum or a minimum.
Okay,
Then you
but
can, oh,
let me say this though. The question was, how do you tell where the function's increasing? And that answer,
oh,
yeah, that answer isn't where the derivative is zero.
no. You have to find a point between the intervals and test to see whether the derivative is positive or negative at those points. If it's
Okay, and which
negative,
one tells you the function's increasing?
if it's positive.
Yes, yes, that was the whole answer.
Oh, sorry.
How can you tell by looking at the derivative that a function is increasing? And the answer is wherever the derivative is positive. How do you tell when a function's decreasing? By looking at the derivative.
When it's negative.
Yeah. And how do you tell by looking at the first derivative where the function has a maximum value?
Well, the maximum value is if it's higher than all the other points you've tested for.
Right. So how do you tell that by looking at the derivative?
I don't know how to explain that.
Somebody jump in and help using the words increasing and decreasing. Maybe I'm just not asking the question well. If I give you a function with two critical numbers, tell me again what critical numbers are, the definition of critical numbers.
The critical numbers are the points where the derivative is equal to zero, and it's usually where the function changes from increasing to decreasing, vice versa.
Okay.
Something happens.
Yeah, you're right. And you almost answered that other question I asked. Now, there's a little bit more to the definition of critical point other than just where the derivative is zero. There are two other things in the definition. What are those two other things?
The function first has to be defined.
Right. If the function's not defined there, it can't be a critical point. So the function has to be defined, and Aiden said the function could be zero. What's the one other missing part?
Or undefined.
Or undefined. All right, so let's say I have some function with two critical numbers, and that means if I call them a and b, f of a and f of b are both defined, and they either make the derivative zero or undefined. So let's say I have found these two critical numbers. I've picked test points in each of these three derivatives, and I have found that to the left of a, the function's derivative is negative. In between a and b, the function's derivative is positive, and then to the right of b, the derivative is negative. How do you look at that and tell where there's a max and a min? Using the words increasing and decreasing.
You can draw a little picture.
Tell me more. What little picture? You mean graph the function?
Yeah.
Well, we're doing this so we can be able to graph the function. I don't have to have the graph of the function to figure out whether a or b are relative max or min. I can tell by looking at this.
Well, the maximum would be at the end of the interval, the right end of the one that's increasing.
That's it. That's it. Where the function stops increasing and starts decreasing. And Mackenzie, I thought that was the little picture you were talking about. When the function stops increasing and starts decreasing, that tells you that there's a relative max at b. And then where the function stops decreasing and starts increasing, that tells you where the function has a relative min. Now, all of chapter 4 is about being able to graph functions better than we could in college algebra or even pre-calculus. And this is just one of the steps. These problems in 4.6, they're going to have parts A, B, C, D, E, F, G, probably H, I, J, K, L, M, N, O, P. And some of the parts are going to be tell where the function's increasing, tell where the function's decreasing, give the points where the function has a relative max, give the points where a function has a relative min, find the domain, find the vertical asymptotes. All of those things are going into what we're doing and will be parts of the problem in 4.6, but 4.3 is just, well, what can the first derivative tell us? And the first derivative can tell us where the function's increasing, where it's decreasing, where it has relative max, and where it has relative min. And yesterday, y'all were supposed to have done basically 1 through 31, and I called it quits there. Most of those were just polynomial functions, so they were easy to differentiate, easy to find the critical points. 33 through 56 had some more oddball problems, and that's why we have a second day on 4.3. They're not just polynomial functions. So what have you tried and not been able to get the right answer to on 33 to 55? Does that mean everybody's done 33 through 55 and totally okay with it? Or does that mean everybody's speaker is on mute?
Can we do number 45?
Absolutely. Ooh, yeah, it's a little bit ugly. 45. What would it take to differentiate that function in number 45?
Product rule.
Yeah, definitely the product rule. Put a dot there if you want. Let's see if this is what you got for the derivative. Is this Miss McKenzie?
No, it's Abby.
Abby, you and Mackenzie sound the same on speaker, but I didn't notice that when I could see your face. You sounded different. All right, so first factor times the derivative of the second. Derivative of e to the ugly is e to the ugly times the derivative of the ugly, and that's just 1. So first times derivative of the second plus the second times the derivative of the first. What's the derivative of the first?
-1.
-1. So I'm just going to change that to a minus. All right, that's the derivative. What did you do next, Miss Abby?
Then I factored out e to x minus 3.
Yeah, I would too, because this is why our goal has been factor completely as possible all along. So I knew that we were coming up to those that we'd need to set equal to 0, and that's easier to do in factored form. So if we factor an e to the x minus 3 out of both terms, we'll have 3 minus x left of the first term and just -1 left from the second term. So factored as completely as possible, that derivative is e to the x minus 3 times 2 minus x. And that's what you got?
No, I was stuck at that point.
No, I meant so far, that's what you have.
Oh, yeah.
Okay. One other thing I didn't think to mention at the beginning, but I told you this is always a good idea to think about the domain of the function. And in these problems in 4.6, that'll be the A part, give the domain of the function. Is there anything that I could not let x be here? Anything that makes the function undefined?
No.
No. So I don't have to worry about that when I'm finding critical numbers anything that makes this 0 or undefined will be a critical number because the function is defined for all values of x. All right, so is there anything that makes the derivative undefined?
No.
No. So we're only looking for what makes the derivative 0. And if I have something factored and set it equal to 0, then I just set each factor equal to 0. So what's the solution to this equation? I'll take the easy one, make you do the hard one. It would have been just a little bit easier. It would have been a hint if I had said, is there any power of e that gives you 0?
No.
No, there's not. So this just doesn't have a solution. So there's only one critical number, it's 2. So that's the only number you'll have to put on your number line and find the sign of the derivative to the left and to the right of 2. So was this the whole thing that was bugging you, Miss Abby?
Yes.
Okay. There's no power of e that gives you 0, so that just doesn't give you a critical point. All right, what else? 30, well, anywhere in 4.3. Since no one is responding that way, let me ask this. Miss Abby, was that your only question?
Yes.
Mr. Aiden?
Yes.
Grace? Miss Grace?
Sorry about that. Yeah, I'm good.
Okay, Dylan?
I think I'm good.
Okay, Ivy?
I'm good.
Joseph?
I'm good.
That's awesome. I thought you might have questions about the absolute value on 37, or maybe the piecewise function on 43, or maybe the inverse trig function on 47. But my video must have been adequate. Let me tell you one other thing then. I know that the hardest thing we've done since maybe the chain rule the first time we saw it is related rates problems. If you are not feeling confident about those, trust me, you're not alone. If anyone does feel confident about those, then I'm kind of surprised. So this morning I looked at Khan Academy. It's just one of the most valuable educational websites that's ever been made. He had a whole unit on related rates problems, and I sent you via email a few minutes ago the link to the introduction to related rate problems, his very first video on those. Khan Academy has come so far in that now not only do they have videos, but you watch a short little video, 5-6 minutes, and then he gives you some practice problems, and then you watch the next video and he gives you some practice problems. So he has a whole unit on related rates broken down that way. He'll do a falling ladder problem and then give you a falling ladder problem. He'll give you an area of a circle problem, and or give you a video and then a practice problem. So it's really, really good. And I sent you the link to the very beginning of that unit, and you can click through it, watch as much of it as you need to. Actually, since you all seem okay on 4.3, I'm gonna loosen up and not put any MyMathLab homework for today, so that you can go back and spend this weekend on whatever you need to spend it on. But I would think that probably related rates problems are the ones that are bugging the most people. You think I'm right in that?
Definitely.
Definitely.
All right, so this weekend, just make sure you have 4.3 finished. Go back and watch some related rates problems on Khan Academy, and then be ready to discuss 4.4, 8 o'clock Monday. Okie doke.
Mhm.
All right. Y'all have a good weekend.
You too.
Yeah.
Bye-bye.
Bye.
Bye-bye.